Earth has a definitive expiration date. In roughly 1 to 3.5 billion years, the sun's expansion will trigger a runaway greenhouse effect. The oceans will boil, the atmosphere will ignite, and the planet will be entirely sterilized. To understand how life might survive this inevitability, we have to look at how we think it began. The standard model of biological history relies on terrestrial abiogenesis, the premise that life emerged exclusively from non-living matter through localized chemical reactions on the early Earth. For decades, scientists have attempted to replicate this localized origin. Classic laboratory demonstrations, like the Miller-Urey experiment, placed simple gases into glass chambers and exposed them to electrical sparks, showing how basic organic material forms in primordial environments. But a growing body of researchers argue that looking exclusively at early Earth is too narrow. They propose that life is a cosmic phenomenon distributed across the interstellar medium rather than being restricted to a single planet. If biological origins are not tied to local planetary chemistry, the search for life's beginning expands. Biology becomes less about a single planet's history and more about how material moves through the galaxy. This concept is known as panspermia. Derived from the Greek words for all and seed, it proposes that life is distributed across the vast entire universe, carried by cosmic dust, by icy comets, and rocky meteoroids. While it sounds like modern science fiction, the concept has deep historical roots. Eminent 19th century physicists, like Lord Kelvin, argued that meteoritic stones from other worlds could act as seed bearers that kick-started the biological record on Earth. Mainstream biology has historically dismissed panspermia as a fringe concept. The primary criticism is that it fails to explain how life actually began, instead simply moving the origins of abiogenesis to an unknown celestial body. That criticism misinterprets the goal of modern panspermia research. The theory does not attempt to answer the precise chemical origin of life. Instead, it tests the physical survival limits of biological material and maps the mechanics of how it navigates the void of space. Rather than a single guess, panspermia acts as a system for testing how biology survives and travels across the void. This table categorizes exactly what biological state is being transported and how. The most widely accepted model among mainstream scientists is pseudo-panspermia, or soft panspermia. The biological state required here is not living cells, but rather chemical precursors, amino acids, nucleobases, lipids, and sugars. This model requires no living organisms to survive the vacuum of space. It relies on comets and carbonaceous chondrites acting as delivery vehicles, raining the chemical alphabet of life down onto a planetary surface to facilitate local abiogenesis. Astronomical observation confirms the scale of this mechanism. Ultraviolet and infrared spectral signatures reveal that nearly 1/3 of all carbon in interstellar space currently exists in the form of organic material. Soft panspermia demonstrates that the universe is efficient at synthesizing and distributing raw biological ingredients. The subsequent question is whether space can successfully transport the living architect that uses them. That stricter proposition is called hard panspermia. It requires that viable, living cellular replicators endure the journey between stellar systems and establish a biosphere upon arrival. One mechanism for this is radiopanspermia, where individual microbial spores are pushed directly through the vacuum, accelerated to high speeds by the radiation pressure of stellar photons. A more heavily researched model is lithopanspermia. In this scenario, biological architecture is encased and shielded within planetary rocks that are ejected into space by massive asteroid impacts. We have physical proof that planetary debris makes this transit. The ALH 84001 Martian meteorite, recovered in Antarctica, features a dense structure capable of shielding internal material from the radiation of deep space. To survive lithopanspermia, an organism must endure severe physical bottlenecks: the G-force of the initial ejection, the deep freeze of the void, and the heat of atmospheric entry. Modern biology has cataloged extremophiles on Earth that can withstand these exact pressures. Combined with verified meteorite impact data, the physical evidence indicates that biological payloads possess the resilience necessary to survive the journey. Critics will often apply Occam's razor here. If interstellar transport is fraught with such physical barriers, the simplest explanation is that life started naturally and easily on early Earth. But the timeline of Earth's early history creates a severe mathematical constraint. The window between the Earth cooling enough to support oceans and the first appearance of cellular life in the fossil record is relatively narrow. This diagram illustrates a probability tree comparing two models. On the left, a model restricted to Earth's 4.5 billion year history. On the right, a distributed origin model utilizing the 13.8 billion year timescale of the galaxy. Researchers like Fred Hoyle and Chandra Wickramasinghe point out that forming functioning enzyme batteries and cellular membranes from scratch requires immense combinatorial chemistry. A localized Earth may not offer enough time or spatial volume for random chance to execute these chemical combinations successfully. In this view, moving the origin off-world isn't about avoiding the question. It's an attempt to gain the massive spatial volume and deep time that proponents argue are required to explain how complex life appeared so quickly on Earth. While natural panspermia relies on the passive mechanics of random impacts, a separate branch of the theory explores intentional cosmic distribution. This is directed panspermia. The concept was hypothesized by prominent scientists, including Nobel laureate Francis Crick, who co-discovered the structure of DNA. He suggested that the complexity of our genetic code could be the result of deliberate seeding by an advanced civilization. Today, the focus has shifted away from whether aliens seeded Earth. The pressing question is how we will handle our own approaching capability to seed exoplanets using laser-propelled interstellar nanocrafts. This conversation is driven by immediate pressures. Anthropogenic existential risks, from engineered pandemics to nuclear war, threaten humanity's long-term capability to act. Philosopher Toby Ord has calculated a probabilistic estimate that gives humanity a 1 in 6 chance of facing an existential catastrophe within the next century. If humans are currently the only terrestrial species capable of developing interstellar transport, our societal fragility creates a ticking clock. This makes galactic biopreservation a practical objective. Executing directed panspermia requires a formal moral framework. Ethicists approach this through biotic ethics, which assigns value to the continuation of the genetic heritage shared by all terrestrial life. This matrix breaks down the desirability of directed panspermia. It cross-references empirical variables, how common life is in our galaxy, against axiological variables, different environmental value theories. The most favorable case emerges if life is exceedingly rare in the galaxy. If life has intrinsic value, and we are alone, expected utility theory suggests we should execute planetary seeding to secure its survival. But there are counter-arguments. The primary scientific objection is the risk of forward contamination. Sending biological payloads could violate planetary protection protocols, potentially interfering with or destroying biospheres native to the target exoplanets. Philosophically, critics raise the risk of suffering. If evolutionary processes naturally result in predation and pain, intentionally spreading wild animal life could multiply that suffering on a galactic scale. To navigate this moral uncertainty, ethicists evaluate the expected outcomes of creating extra life. As this table shows, if an agent assigns even partial value to the existence of more life, the choice to seed other planets yields a net positive expected value. Directed panspermia forces us to decide on a specific role for our species. We can remain a localized occurrence, or we can use our technology to act as a preservation mechanism for the life that evolved here.